So here we are going to learn about Euclidean algorithm. It is used to find GCD, right, the greatest common divisor between any two arbitrary numbers. So by numbers here I mean integers. What's the idea behind this, right? So how did we envision this algorithm, right? So given any numbers a and b, right, any arbitrary numbers a comma b, a can be written as some a times some quotient into b plus r, where r is the remainder. Okay, when we try to divide a with b and q is the quotient. So the condition that we have is r should be strictly less than b and it should be greater than or equal to 0. If d divides a and d divides b, right, so that's how this symbol is read. We can write a as some quotient into d and b as some other quotient into d. And we can rewrite this equation this way. So r is equal to a minus some q times b. If we substitute these here, we can take d as common. We can write so k minus q times l. So k is an integer, q is an integer, l is an integer, d is also an integer. So r is written as a product of d times some other integer, which means, okay, from this we can conclude d divides r. Yeah. So with this idea, right, so we can extend the algorithm like this. Let's say r0, let's rename a to be r0 and b to be r1. Right, so we can write r0 is equal to some q0 times r1 plus r2. So we have just learned that the GCD of r0 comma r1 should be equal to GCD of r1 comma r2 because of this fact. If d is the GCD of a and b, it implies d divides a and d divides b, so d also should divide r. So with this we can extend that GCD of r0 comma r1 should be equal to GCD of r1 comma r2. And we can rewrite r1 as some quotient times some quotient q1 times r2 plus r3. And if we expand this, we will get something like this. Okay, rn plus 1 is equal to some quotient n times r. So quotient n minus 1 times rn plus 0. I'm very confident that if we continue this algorithm, right, so if we continue these steps one by one, at the end I will arrive at 0. How am I so sure about it? Because at every step we have this invariance, right? So any time you try to divide we're trying to find a remainder, we can be sure that r2 should be strictly less than r1 because that's how we have defined the reminders, right? And similarly in this step we can be sure that r3 should be strictly less than r2. Okay. For simplicity, let's just imagine we are only working with positive integers. Okay, but even if we are working with negative integers, we are actually, we restrict our reminders to be strictly positive. Okay, if you remember how we have defined the symbols, right? Define the symbols and this equation. So at every step we are getting a smaller and smaller integer. So at the end we will arrive at 0. That's the idea. So what is the time complexity of this algorithm? Okay, so this, I'm not going to teach you complexity analysis here, okay, but this is good to know. Because in Bitcoin, we are going to work with 256 bit integers. Okay, and if you are going to use Euclidean algorithm to find the GCD or to find the multiplicity inverse, there will be at most 256 there will be at most 256 steps. Okay, this is something like a logarithmic factor, but you can try to look it up, right? The term that you have to search for is what is the time complexity of a Euclidean algorithm, and you can come to this conclusion, right? So How does this work in practice? Let's take this example. Okay, so we are going to find the GCD between the two numbers 252 and 105. So 252 can be written as 2 times 105. What is the remainder? 210. Okay, so 252 minus 210 will be 42. So remainder is 42. I mean, you can follow along with the calculator. Okay, and 105 can be written as 3 times, no, 2 times 42 will be 84. Okay, so 84 plus 21 will be 105. So 21 will be the remainder. And 42 is 2 times 21 plus 0. It's quite fast. We arrived at the GCD at just 2-3 steps. Okay. So what is a GCD? 21 is a GCD. Okay, because 21 divides this 42 exactly. So if we continue this step, then Rn, right? So this is the Rn, I mean, whatever the n is, this will be the GCD. Okay, and as you can see, 252 divided by 21, okay, what it will be? It will be 1 times 42, it will be 12, and 21 times 5 is 105, and 21 divides both of these numbers, and you can verify that there is no greater number which divides both of them. Okay, you can go on to verify. The best possible way to verify is just factor things out. So this is 7 times 5 times 3. 252 will be 7 times 3 times 12, yeah, which is 4 times 3. Yeah, from this you can easily conclude that 7 times 3 is the common factor between both of them. Okay, so 21 is the answer. So how will you code this algorithm? It's pretty simple. So when you're trying to find the GCD of a comma b, you're going to iterate through a loop, okay, and you're going to find the remainder of a and b, and that will be b, okay, and you're storing a to be the temporary value, which is the previous value. Take some time, compare this with the algorithm that I explained here in every single, like how we are shuffling R1 and R2 in every single step. Okay, think about it and try to understand this, right? And you can create this algorithm in your own favorite programming language, and you can play around with these numbers. You can add prints or logs in between to better visualize how this algorithm works. Okay, that's it.